All right, let's talk about AI. It's so easy to get completely captivated by the model itself, right? The magic of it. But here's the thing, building a real AI product, one that people can actually count on, well, that's a whole different ballgame. Today, we're going to look past all the hype and get into what it really takes to build solid AI systems. And spoiler alert, it's a story all about software engineering.
So let me ask you a question. When you picture building an amazing AI application, what's the first thing that pops into your head? For most of us, it's the model, the algorithm, the accuracy stats, the complex neural network. But what if I told you that's just the very, very tip of the iceberg? You see, there's this really common way of looking at machine learning models as a kind of black box. You shovel some data in one end, some mysterious, magical stuff happens inside, and poof, an answer comes out the other side. Now, that view isn't exactly wrong, but it is dangerously incomplete. It totally ignores the massive, complex machinery that you need to build around that black box to make it useful and safe in the real world.
And that brings us right to the heart of the matter. It's this fundamental clash of cultures, this tale of two mindsets. You've got the world of traditional software engineering on one side and the world of machine learning on the other. And now they have to figure out how to work together.
Okay, let's really break this down. In one corner, you have software engineering. This is a world built on structure, on predictability. Engineers are all about functional correctness. A function has to pass its tests 100% of the time. If it fails even once, that's a bug. It's broken. It needs to be fixed. But then in the other corner, you have machine learning, which is, by its very nature, experimental. It's all about statistics. For a data scientist, a model that's 85% accurate can be a massive success. But think about it. That also means it's failing 15% of the time. These two worlds have completely different definitions of what success even looks like. And this quote just nails that culture clash. An engineer looks at 63 failures and immediately thinks, whoa, this thing is broken. We can't ship this. But a data scientist sees those same 63 failures, probably in the context of thousands of successes, and thinks, hey, this model is working great. Now, neither of them is wrong. They're just speaking completely different languages when it comes to quality and what it means for something to be done. So this leads us to a really important change in perspective. We have to stop focusing just on the model and start thinking about the entire system. I love this analogy of the AI iceberg, where the model is just that small, visible tip sticking out of the water. So let's get our terms straight. An ML model, that's the algorithm. That's the piece of code trained to do something specific, like spot a cat in a photo. But the ML system, that's the whole shebang. It's the model, plus the code that gets the data, cleans the data, the servers that actually run the model, the tools that watch it to make sure it's behaving, and the interface the user actually interacts with. And this isn't a small difference we're talking about. This quote from a really famous paper by Google researchers makes an absolutely incredible point. The actual ML code, the magic part, is often just a tiny little box in a huge diagram. The vast majority of the code, the work, the complexity, that's all classic software engineering. It's data verification, feature extraction, monitoring, analysis tools, all of it. Okay, so if the model is just one small part of this whole thing, and we know it's never going to be perfect, how in the world do we build products we can rely on? Well, this is where a pretty radical shift in thinking has to happen. We have to start engineering for failure. Here's the key idea. We have to start treating the ML model as an unreliable function. Think about it. In normal programming, a function has a contract. You give it 2 + 2, you expect to get 4 back, every single time. In ML model, it makes no such promise. It might be right 99% of the time, but that other 1% can cause real problems. This just shatters our traditional ideas about how we build and test software from smaller parts.
So how do we handle this? How do we build something solid on top of an unreliable foundation? We have to zoom out. We stop trying to perfect this one little model in a vacuum, and instead we start designing the entire system to be resilient, to be fault-tolerant. This is what it means to adopt systems thinking.
Let's use a really simple analogy to make this super clear. Imagine you're building a smart toaster. It has a fancy AI model that uses a sensor to predict the absolute perfect piece of toast. But what happens when that AI messes up? How do you stop it from burning your kitchen down? This is such a brilliant way to explain the solution. It's all about defense and depth. Layer 1, you have the model, trying its best to be smart, but you don't trust it 100%. So layer 2, in the software, you add a dead simple non-AI rule.
A timer. No matter what the model says, shut off after 3 minutes. And then for your final safety net, layer 3 is in the hardware itself, a physical thermal fuse that just cuts the power if things get dangerously hot. See, the toaster is safe not because the model is perfect, but because of all the smart engineering built around it. And this idea of defense in depth applies to pretty much any AI system. For example, you can have a human in the loop. In a hospital, an AI might flag a potential issue on an X-ray, but a human radiologist has to confirm it before any action is taken. You can also build simple guardrails. These are like the toaster's timer, simple checks in the code. If your model predicts a product should cost -$5, a guardrail would catch that nonsense before a user ever sees it. You can make actions undoable. If an AI recommends the wrong movie, who cares? You just click undo. That builds a ton of trust. And finally, you absolutely need robust mistake detection and recovery. You've got to be monitoring your model in the wild to see when it starts making mistakes, so you can step in and fix things before they become a real disaster. Now, this whole systems thinking approach forces us to think about something that often gets ignored in the race to train a model: the system's architecture. Where the model actually runs is just as important as how accurate it is. One of the biggest architectural decisions is, should the model run on the user's device, like their phone, or should it run on a server in the cloud? And the trade-offs here are huge. Running on-device gets you super low latency, it works offline, and it's great for privacy because the data never leaves the phone. The catch? You're limited by the power of that device. On the other hand, running it in the cloud gives you almost unlimited horsepower for giant, complex models. But that comes with higher latency, it won't work without an internet connection, and you have to think about the privacy of sending user data to a server. There is no one-size-fits-all answer here. The right choice depends entirely on what's important for your product. Is it speed, privacy, or cost? So what does this all boil down to? It means we need to change the entire conversation around building AI. The real competitive advantage in the future isn't going to come from having a model that's 1% more accurate. It's going to come from mastering software engineering for AI, what you could call SE for AI. So let's just quickly recap the big ideas. First, an ML system is not an ML model. The model is just one piece of a much, much bigger puzzle. Second, since failures are going to happen, you have to design your whole system to handle them without falling apart. Third, this means you have to think way beyond just accuracy. Things like speed, privacy, and cost are often way more important. And finally, and this is the big one, never ever trust only the model to keep things safe. You always need multiple layers of protection. At the end of the day, the future really belongs to the folks who get this right. The teams and the companies that shift from being model-obsessed to being system-focused. The ones that master these engineering principles, they're the ones who are going to build the products that we all can actually trust and rely on. So I'll just leave you with this one question to chew on. We know for a fact that your AI model, no matter how clever it is, will eventually get something wrong. The real question isn't if it will fail, but when it fails. And is your system actually engineered to survive it?